Hi everyone, this is our video for test 4, the problems past number 82, I believe, so 82, 84, 86, something like that. So this says, if f is a continuous function on the closed interval a to b, which of the following must be true? So really all they told you was the function was continuous. All they told you, they did not tell you was, cannot assume, this is really important, we cannot assume that f is differentiable. So the first part says there is a number c on the open interval ab such that f of c is equal to 0. Well, just because the function is continuous doesn't mean we have to have f of c ever equaling 0. Maybe the function's totally above the x-axis. Maybe it's totally below. Maybe it could just totally be above or below the x-axis, and then we're fine. So then b says there is a number c in the open interval a to b such that f of c is sandwiched between f of a and f of b. Well, I mean, there's many counterexamples. One counterexample is just to take any line with slope 0. And on that, we know that f of a equals f of b, which equals f of x everywhere. It's all the same height. So that's out. Choice C says there is a number c in the closed interval a to b such that f of c is greater than or equal to f of x. This is true. This is true even on the constant function because they don't prescribe that the f of c has to be greater than than any other f of x. What they prescribe is greater than or equal to. This is the extreme value theorem coming into play here, which says that on a closed interval, a continuous function has an extreme value. So this is true no matter what. D says there is a number c on the open interval f from a to b such that f prime of c is equal to 0. Even if the function were to be differentiable, that's not even guaranteed. It certainly isn't guaranteed for any continuous function. So for example, here's a function where the derivative is never 0. And E, there exists a number c from a to b such that f prime of c is equal to the ratio of the rate of change from a to b. Again, not true if the function's not differentiable. So for example, if we take the last example I just drew, if I look at the secant line, nowhere along the graph will I find a tangent line slope that's parallel to it. So that's out. Choice C is the answer. Whoops, hold on one second here. Why that's all the way down there, but it is. So anyway, as I'm changing this, this is number 84, and it says, the graph of f prime, the derivative of f is shown above, on which of the following intervals is f decreasing? Well, f decreases precisely when f prime is less than 0, and on the graph that means f prime graph is below the x-axis. So where is this thing below the x-axis? Well, let's see. If we travel along the graph, we're below the x-axis from 0 to 2, then we're above it up to 4, and then we're below it to 6. So I would say the interval 0 to 2 and 4 to 6 should be the answer. And that's choice E. Alternatively, you can draw your number line, which would look something like this. From 0 to 2, you would have negative for f prime, based on the f prime number line. From 2 to 4, f prime is positive. From 4 to 6, f prime is negative. And 6 to 7, f prime is positive. Okay. All right, next question, number 86. The function f is continuous and differentiable on the closed interval of 3 to 7. The table above gives selected values of f on this interval. Which of the following must be true? Number 1 says the minimum value of f on 3, 7 is 12. Well, what's to stop me from going, all right, maybe at 5.5, the value of f is 10. Well, then the minimum wouldn't be 12. Okay? Choice 2 says there exists c from 3 to 7 such that f prime of c is equal to 0. This might be helpful to draw out. So At 3, wow, that's bad. Hold on 1 second. I'm doing this at home. I'm not doing this on my smartboard. So just bear with me for a moment here. I like doing this on the smartboard better, but unfortunately, I can't afford a $5,000 piece of equipment, nor can I afford the wall space. So, if we draw this thing, okay, so at 3, we're at 20. At 4, 17. At 5, we're at 12. I know I'm not really drawing this to scale, but that's okay. 6, we're at 16. So we're somewhere there. And 7, we're at 20. So our simple graph would be something like this, say. That would be the simplest graph. And then something maybe more complicated would be something like this. In either case, you'll see that you have to have a place where f prime of c is equal to 0. You have to have a place where the tangent line is horizontal, even on the more complicated graph and even on the more simple graph. Whoops. Simply because I have these two equal endpoints. And the average rate of change between two equal endpoints is 0, and therefore the average rate of change has to be equal to the instantaneous rate of change somewhere. The way I just described it is an application of the mean value theorem, or you can say, well, this is Rolle's theorem, which is just a specific case of the mean value theorem, saying if I have two equal endpoints, I have to turn around somewhere, and at that place, I have to be differentiable. So this is true. F prime of x is greater than 0 from 5 to 7. Well, I think if you see the second example that I drew, right here on this interval, I'm not convinced that f prime there is positive. In fact, it may even be 0 or negative. Or even if you just exaggerate this a bit, even if you just exaggerate my graph a bit, you can take this graph, the purple, well, the more complicated one, and exaggerate it a bit. Maybe send it up here and then down there and then up back again. And therefore you'll see you do not have to have f prime being greater than 0 on that whole interval. So 2 only is the answer. All right, number 87. The figure above shows the graph of f prime again. On the open interval negative 7 to 7, f prime has 4 zeros. It says how many relative relative maxima. Underline that. Sorry, let's pause this for a minute. Here I would suggest drawing a number line. This is f prime, and we're going to draw an f prime number line based on it. So our zeros are, say, here, 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 and here. And before you get to the first 0, the derivative is negative. Then it's positive. Then it's 0, but only for that brief moment of time, and it goes back to being positive, the derivative. Then the derivative is negative, and then after that, the derivative is positive. So we want relative maxima. We want places where f is going to be at a maximum. So if I think of f down here for a moment, f is decreasing, then it's increasing, then it continues to increase, then it begins to decrease, and then increase. We're on the open interval, so we're only looking at numbers inside strictly between negative 7 and 7. And I think you'll see that right here is the only maximum. This is a min. This point is neither a min nor max, and this is a min. So only at this one location do we have a maximum. 89 says the table above gives the values of the differentiable functions f and g at their derivatives at 1, x equals 1. H of x is this long complicated thing, then h prime of 1 is. Well, we need to come up with h prime of x. H is a product of two functions, so I will use the product rule. So over here I'm going to break up my pieces. Derivative of 2f of x plus 3 is 2f prime of x plus nothing. The derivative of 1 plus g is g prime. And so h prime of x is going to look kind of complicated, but we'll write it nevertheless. We're going to have this thing times g prime. So 2f of x plus 3 times g prime of x plus 1 plus g of x times 2f prime of x. And now it's just incumbent upon us to be careful and plug in 1 for this. So we get 2f of 1 plus 3 times g prime at 1 plus 1 plus g of 1 times 2f prime at 1, which is going to be, let's see if we can do this within limited space here. 2 times f prime at 1. Well, f prime at 1 is negative 2. 2 times negative 2 is negative 4, plus 3 is negative 1. G prime at 1 is 4, plus 1 plus g of 1. G of 1, consequently, when the chart is negative 3. 1 plus negative 3 is negative 2. Times 2 times f prime at 1. F prime at 1 is negative 2. 2 times negative 2 is negative 4. So this looks like it comes out to be negative 1 times 4 is negative 4. Negative 2 times negative 4 is positive 8. And I think we get an answer of 4, which is not correct. So I have to go back and see what I did wrong here. Let's see. And I believe I found what I did wrong here, which was this. F of 1, I was looking at f prime of 1. F of 1 was 3. So if f of 1 is 3, 2 times 3 is 6 plus 3 is 9. And now we get, instead of negative 4, we get 36 plus 8, which is 44. And that I have I'm pretty confident is correct. All right, number 90. Let me make this a little bigger. Number 90 says, well, I'll make it bigger, I'll read it to you. The functions f and g are differentiable for all x. F of g of x is x and g of f of x is x. What this implies here, this statement implies that f and g are inverses. That's what inverses do to each other. They undo each other. So this means that f inverse equals g. So f of 3 is 8 and f prime of 3 is 9. They want the values of g of 8 and g prime of 8. And this is where that little chart that I showed you kind of comes in handy. So we have f and we have g, which is f inverse. We know f of 3 is 8. Well, since g is the inverse, that means g of 8 is 3. Then we knew f prime at 3 was 9. And so g prime at 8, at the x value, is the reciprocal of f prime at 3. So g prime of 8 will be 1/9. So g of 8 will be 3, based on the point. G prime of 8 will be the reciprocal of this derivative. So g prime of 8 is 3. And, g of 8 is 3 and g prime of 8 is 1/9. Choice E. And that's it.